Before we go to the biological pump as the next hypothesis for explaining the glacial deglacial CO2 changes, we have to run through this chemistry part, which is always quite intricate, and I always have to look it up to make sure that I don't screw it up. Okay, so Archer actually does a good job in the book. You should read it up. Let's start with it. Ideally, after air and water have had time to equilibrate, the amount of CO2 in the gas phase will go up and down in direct proportion to any changes in the concentration of the dissolved CO2 in the solution, the water phase. This is known as Henry's law. So this is ideal situation where the partial pressure of CO2 in the water is proportional to the constant times the total CO2 gas phase in the water. Okay, obviously the situation is never ideal because CO2 gets interacting with others in the water and it gets moved around, as we already seen, into carbonic acid, bicarbonate, carbonate, and so on and so forth. So we're not talking about the ideal situation anymore. So CO2 then combines with water in a hydration reaction. So you have a dissolved CO2, hydrated CO2, and there is a hydration dissolved CO2. So they are essentially the same, but slight difference. So CO2 plus H2O gives H2CO3 in equilibrium. That's the reaction. So now we, instead of just looking at CO2 aqueous, we have to look at the total CO2 as aqueous plus the hydration reaction. So you write that as H2CO3 star. So now PCO2 of the water is proportional to H2CO3 star, which is the Henry's law constant Kh prime. So that's the Henry's law, right? PCO2 is important because as upwelling happens, as biology happens, biology can draw down CO2, reduce PCO2. Upwelling can bring carbon-rich water to the surface and increase surface water PCO2, and it's the difference between the seawater PCO2 and the atmospheric PCO2 that's going to determine which way the CO2 is going to go, into the ocean or out of the ocean, right? Just like opening a Coke can. Okay, so the other reactions that happen very, very quickly that are in equilibrium essentially is H2CO3 moving into H+, so releasing an H+, which is where the acidification comes from, and move it into bicarbonate. Then bicarbonate moves into CO3-, the carbonate ion, and another H+, right? So this is where the CO2 dissolution gives us reduction in pH or acidification of the water. And there are many details, like because of this, CO2 amount in the water can be much, much higher than bicarbonate, whereas carbonate tends to be 10 times higher than CO2 because of all these quick reactions that keep moving things around. But as we will see, as you increase CO2, you're going to use up CO3-, plus this released H+ ion, which is very hungry and wants to react with somebody or the other, is going to start splitting calcium carbonate to produce CO3 to go use itself up. The proton is going to be taken up by CO3-. Okay, so you can write the equilibrium constants, or the these are called dissolution constants. Let me make sure. I'm not a pure chemist, so I have to be careful with me. Okay, so these are the first and second dissociation constants, K1 prime and K2 prime, which are written directly from these reactions. So these are concentrations, the square brackets. So H2CO3 divided by H++ times HCO3- equal to K1 prime. You know, I think from your basic chemistry how we go from there to the dissociation constants, and similarly for the second reaction, right? So the best way to think about it then in terms of how CO2, increasing CO2 is going to lead to the loss of carbonate ion and then splitting of calcium carbonate to produce more carbonate ions, which means reduce the saturation of calcium carbonate, which means the coral reefs and other calcium carbonate shell forming animals like forams and coccolithophores are going to start melting, dissolving, because you are moving the reactions around this way. Okay, so CO2 interacts with CO3 plus water to give us two molecules of moles of bicarbonate. Okay, so the net there can be written for H plus, which is our pH control, as H2CO3 concentration divided by K1 prime from this reaction, and this can be summarized easily in this way, that the hungry H plus that is getting released here is going to basically want to interact with this and is going to split or dissolve calcium carbonate. So if the water is super saturated with calcium carbonate, then the coral reefs, forams and coccoliths don't have to worry about their shells dissolving, whereas if increased CO2 and H plus and so on begin to perturb the saturation, then the calcium carbonate is going to split up this way. That's the main thing to remember. Loss of carbonate ion is what is the main acidification impact. So how will changes in ocean chemistry affect marine life? So CO2 absorbed in the from the atmosphere, CO2 plus H2O plus CO3 minus is going to give us bicarbonate. So increasing CO2 is basically going to draw down by the carbonate ion, which is going to make life difficult for species that need the calcium carbonate. That's the main story. Okay, you can read some good papers that are there on it. So there are all kinds of non-linearities involved in here. For example, if you take two samples of seawater with different amounts of carbonic acid in them, dissolved CO2 in them, and if you mix them, you are not going to get the average concentration of H2CO3 between the two because of all these reactions. It's like mixing two seawaters with the same density but different temperature and salinity. Because of the non-linearity of the density, you're going to end up with average temperature, average salinity, giving you a second density. It's called cabling. So similar things happen here. So essentially we will need for modeling purposes, for example, the properties of the ocean carbon cycle, which are conservative. So for that we basically end up taking total DIC and total alkalinity. Maybe I'll leave it to the next podcast because it's going to get too long otherwise, but just remember these equations of dissolving CO2 into the water, hydration, reaction of H2CO3, which quickly goes into HCO3 minus plus H plus, and then HCO3 minus goes into H plus plus carbonate, or CO3 minus minus. Okay, so this dissolving CO2 release of H plus is going to reduce the pH of the water, right? Because pH is just minus log of H plus concentration, so pH is going to change. But what does it mean in terms of alkalinity? Turns out alkalinity is a conservative quantity as well for mixing of water masses and advection of water masses. So the models rely on these conservative quantities, as we will see in the next podcast.